Training GPT-4 cost over $100 million. Not the research, not the salaries, just the electricity and GPU time to run the training loop. And here's what's wild. Most of that compute is spent doing one thing over and over, predicting the next word, getting it wrong, and adjusting billions of tiny numbers by a fraction of a percent. Do that a few trillion times, and somehow you get a system that can write poetry, debug code, and explain quantum physics. How does turning prediction errors into intelligence actually work? Let's break down the three things every LLM needs: data, compute, and scale, and why the balance between them determines everything. Think of training an LLM like raising a genius child with infinite reading time. You need three things: books to read, that's your data; a brain fast enough to process it all, that's your compute; and you need to know how big that brain should be, that's scale. These three pillars are in constant tension. More data means you need more compute. Bigger models need both, and the relationship between them follows surprisingly predictable mathematical laws that we'll unpack throughout this video. Let's start with data. Modern LLMs are trained on text scrape from essentially the entire internet. Common Crawl alone contains over 250 billion pages, petabytes of raw text. But here's the thing. Most of that is garbage. Duplicate content, spam, broken HTML, cookie notices repeated across millions of pages. The real art of training data isn't collection, it's curation. Companies like OpenAI and Anthropic employ entire teams just to filter and clean this data, because training on garbage produces garbage. The data pipeline typically works in stages. First, you run deduplication, removing identical or near identical documents. This alone can cut your dataset by 30 to 50%. Then comes quality filtering. Language detection removes non-English content if you're training an English-focused model. Heuristic filters remove pages that are mostly code, mostly numbers, or have suspicious patterns. Some teams use smaller ML models just to score content quality before the main training even begins. Before any training happens, text needs to be converted into numbers. That's tokenization. Modern LLMs use subword tokenization, typically BPE or byte pair encoding. The word understanding might become 3 tokens: under, stand, ing. This lets the model handle words it's never seen by breaking them into familiar pieces. A typical vocabulary is 50 then to 100 tokens. Every token gets converted to an ID number, and those numbers are what the model actually sees and predicts. Here's a counterintuitive finding from recent research. Data quality beats data quantity almost every time. The LLM models from Meta were trained on only 1 to 2 trillion tokens, far less than some competitors, but achieve better results by being extremely selective about what went in. The 5 models from Microsoft take this further, using carefully curated textbook quality data to train models that punch way above their weight class. The lesson? A smaller, cleaner data set often outperforms a larger, messier one. Now let's talk compute. Training LLMs requires GPUs, specifically NVIDIA GPUs. Why not regular CPUs? A CPU is like a genius mathematician who can solve any problem, but one at a time. A GPU is like 10,000 average mathematicians working in parallel. Training involves doing the same operation, matrix multiplication, trillions of times across different data. That's perfect for GPUs. The H100, NVIDIA's current flagship, can perform nearly 2,000 trillion operations per second for the specific math LLMs need. And you need thousands of them. A single H100 can't train GPT-4. You need clusters. thousands of GPUs working together. This is distributed training, and it's an engineering nightmare. The model itself might not even fit on one GPU, so you split it across many. That's model parallelism. You also split your training data across GPUs. That's data parallelism every fraction of a second. These GPUs need to sync their learnings through high-speed interconnects. Any GPU failing, any network hiccup can corrupt your entire training run. This is why AI labs spend millions on infrastructure alone. Let's demystify what happens in a single training step. The model sees a sequence of tokens, say a sentence with the last word hidden. It predicts what that word should be based on its current weights. Billions of numbers that define its behavior. If it predicts dog, but the answer was cat, we calculate a loss, a number representing how wrong it was. Then backpropagation kicks in. We trace back through the network, figuring out which weights contributed to the mistake. Finally, we nudge each weight slightly to make cat more likely next time. Repeat this billions of times, and patterns emerge. That weight nudging process is gradient descent, and it's beautifully simple in concept. Imagine you're blindfolded on a hilly landscape, trying to find the lowest valley. You can't see, but you can feel which direction slopes downward. You take a small step that direction, repeat until you stop going down. That's gradient descent. The landscape is the loss function, a surface in billions of dimensions. The slope is the gradient, calculated by backpropagation. The step size is the learning rate. Too big and you overshoot. Too small and training takes forever. What makes transformer-based LLMs special is self-supervision combined with attention. Self-supervision means we don't need humans to label every example. We just mask words and have the model predict them. The internet becomes our infinite dataset of free training examples. Attention lets the model decide which words in a sequence are relevant to predicting the next one. When predicting after the capital of France is, attention learns to focus heavily on France and capital rather than the and of. This selective focus is what enables language understanding. Let's talk real costs. Training a frontier model today requires 10,000 to 25,000 high-end GPUs running for weeks or months. A single H100 costs around $25,000 to buy. Renting one costs $2 to $4 per hour. Do the math. 10,000 GPUs running for 30 days at $3 per hour is $21 million just in compute. Add electricity, cooling, engineering salaries, failed runs you have to restart, and you're easily at 50 to 100 million for a single successful training. This is why only a handful of companies can play this game. Here's where it gets fascinating. In 2020, researchers at OpenAI discovered scaling laws, mathematical relationships that predict model performance based on three variables: model size, dataset size, and compute budget. Double the compute, and loss decreases by a predictable amount. These aren't vague trends. They're precise power laws that hold across 6 orders of magnitude. This means before spending 100 million on training, you can run small experiments, plot the results, and predict almost exactly how the big model will perform. Scaling laws turned AI from an art into something closer to engineering. Scaling laws also tell us how to optimally allocate a compute budget. The Chinchilla paper from DeepMind showed that most models were undertrained, too big for their data budget. For optimal performance, model parameters and training tokens should scale equally. A 70 billion parameter model should see about 1.4 trillion tokens. This insight shifted the industry. Instead of racing to build the biggest model, teams started training smaller models longer. It's not just about size. It's about the right balance between brain size and experience. Everything we've discussed so far is pre-training, teaching the model to predict text. But the model that emerges is a random text generator, not a helpful assistant. That's where fine-tuning and RLHF come in. First, you fine-tune on curated instruction response pairs. Questions paired with ideal answers. Then RLHF, reinforcement learning from human feedback, trains the model to prefer responses that humans rate highly. This is a much smaller, cheaper process than pre-training, but it's what transforms a prediction engine into something that actually tries to help you. Behind every successful training run is infrastructure you never hear about. Checkpointing, saving model state every few hours so you can restart from there if something fails. Mixed precision, using 16-bit floats instead of 32-bit to double speed while maintaining accuracy. Gradient accumulation, simulating larger batch sizes than memory allows. Careful learning rate schedules, starting high, gradually decreasing. Custom data loaders that ensure GPUs are never waiting for data. This engineering work is why top AI labs employ as many infrastructure engineers as researchers. There's a growing concern in the AI community. We might be running out of data. Human-generated text on the internet is finite, and models are approaching having trained on most of it. We're also hitting diminishing returns. Scaling laws suggest each improvement costs exponentially more. So what's next? Synthetic data generated by existing models is one approach, but it risks model collapse. Multimodal training on images and video unlocks new data sources. And efficiency improvements, better architectures, smarter training algorithms can squeeze more from existing resources. So that's the complete picture. LLM training is a massive coordination problem. Collecting and cleaning petabytes of text data, distributing computation across thousands of GPUs, and navigating a high-dimensional optimization landscape for weeks on end. It's expensive, it's technically brutal, and it requires getting 1,000 things right simultaneously. But when it works, you get something genuinely remarkable. A system that learned language patterns from the entire internet, crystallized into weights, ready to generate human-like text. Understanding this process helps you see both the power and the limitations of these systems. Let's recap what you've learned. First, LLM training requires massive, carefully curated datasets. Quality matters more than quantity, and data cleaning is as important as the training itself. Second, the compute requirements are staggering. Thousands of GPUs working in perfect sync, costing tens of millions of dollars for a single training run. Third, scaling laws let us predict model performance mathematically, transforming AI training from guesswork into engineering. Next up in our AI series, we're diving into Transformer Architecture Explained, the actual neural network structure that makes all of this work. Subscribe and hit the bell so you don't miss it. And I want to hear from you. What surprised you most about how LLMs are trained? Drop it in the comments. I read every single one.